On December 9th, 2024, the head of Google's Quantum AI lab stood in front of cameras and said something that no serious physicist says lightly. He suggested that a chip sitting on a lab bench in Santa Barbara, California, may have just produced evidence that reality itself branches into countless parallel versions every single moment, and that his machine's calculations might be happening across many of those versions at once, not just in the one universe we experience. His name is Hartmut Neven. He isn't a fringe theorist. He runs one of the most well-funded quantum computing programs on Earth, and he said this about a real result, published in the journal Nature, that any physicist on the planet can read for themselves right now. Stay with me, because what Google's new quantum chip actually did, and what one of its own creators is now saying it might mean, is stranger than almost anything you'll find in a science fiction script, and every part of it is real. Let's start with the chip itself, because you need to understand exactly what it is before you can understand why its results are shaking up a 30-year-old problem in physics. Willow is a superconducting quantum processor, Google's newest, built in the company's own dedicated chip fabrication facility, containing 105 qubits arranged in a precise grid. To understand why that number matters, you first need to understand what makes a qubit fundamentally stranger than the bits inside your phone or laptop right now. A classical bit is either a 0 or a 1, clean answer at a time. A qubit, thanks to a real experimentally proven property called superposition, can exist as a blended combination of 0 and 1 simultaneously, a genuine physical fact about how quantum particles behave, not a metaphor. Link multiple qubits together through a second property called entanglement, where the state of one particle becomes correlated with another regardless of the distance separating them, and you get a system capable of exploring an almost incomprehensible number of possible answers to a problem all at once, instead of checking them one at a time the way your laptop has to. That power comes with a brutal cost, and it's the exact cost that's kept quantum computing stuck in laboratories for nearly 3 decades instead of reaching your pocket. Qubits are almost unbelievably fragile. The tiniest disturbance, a stray vibration, a fluctuation in temperature, even background radiation from space, can collapse their delicate quantum state and introduce an error. And here's the problem that haunted the entire field since the 1990s. In ordinary computing, adding more parts to a machine doesn't usually make it less reliable. In quantum computing, every additional qubit is another fragile point of failure, and for decades, more qubits generally meant more errors, not fewer, the exact opposite of what you'd want if you were trying to build something actually useful. Physicists had a theoretical fix for this, something called the surface code, a method of grouping many unreliable physical qubits together, so they collectively behave like one much more stable logical qubit. It was elegant on paper. Nobody had ever proven, in a real working machine, that scaling this approach up would actually make things better instead of worse. That's the specific, well-documented 30-year-old problem Willow was built to finally settle. And in that same December 2024 announcement, published under the title Quantum Error Correction. Below the surface code threshold, Google's research team announced they'd done exactly that for the first time in the field's history. Not a simulation, not a theoretical projection, an actual physical working demonstration, sitting in a lab, that error correction in quantum computing genuinely works at scale. And it's the reason a single, controversial sentence from the man who built it has physicists across the world still arguing about what reality actually is. Here's exactly what Google's team actually measured, and why it mattered enough to make physicists sit up straight. The research team, led by scientists including Michael Newman, tested grids of physical qubits at increasing sizes, starting at a modest 3 by 3 arrangement, then scaling up to 5 by 5, and finally to 7 by 7. And every single time they made the grid larger, something happened that had never been cleanly demonstrated before in a real device. The error rate didn't increase, it was cut in half. Physicists call this exponential error suppression. And crossing that specific threshold, where adding more qubits genuinely makes the system more reliable instead of less, is what researchers refer to as operating below the surface code threshold. It's considered one of the most significant engineering milestones in the entire history of quantum computing, precisely because it proves, in hardware you can actually point to, that this technology can theoretically scale towards something genuinely useful instead of collapsing under its own fragility as it grows. Willow didn't stop at proving error correction works, though. Using the same benchmark test Google first introduced back in 2019, called random circuit sampling, essentially verifying the output of a quantum random number generator, Willow completed a calculation in under 5 minutes that Google's team estimated would take Frontier, one of the fastest classical supercomputers currently operating on Earth, roughly 10 septillion years to replicate. Written out, that's a 1 followed by 25 zeros, a number so large it dwarfs the current estimated age of the entire universe, roughly 13.8 billion years, by an almost incomprehensible margin. And that's the exact context in which Hartmut Neven made his comment. During the announcement, Neven suggested that Willow's benchmark performance lends support to the many worlds interpretation of quantum mechanics, a real decades-old idea in theoretical physics first proposed by physicist Hugh Everett back in the 1950s. The many worlds interpretation argues that every quantum event doesn't just produce one outcome, it produces all possible outcomes simultaneously, each one, branching off into its own separate, equally real universe. Under this interpretation, there isn't one timeline where you read this sentence and a separate hypothetical where you didn't. Both actually exist, just in universes that have branched apart from each other. Neven's argument was that Willow's speed only makes intuitive sense if you imagine its computation isn't happening in some clever, compressed way inside one universe, but is instead effectively happening across an enormous number of these parallel branches simultaneously, with Willow essentially harvesting the combined computational power of realities we can't directly observe. It's important to say plainly that this remains a genuinely contested interpretation, not a settled scientific fact. Many respected, physicists favor entirely different explanations for the same quantum behavior that don't require multiple universes at all. But Neven's statement is real, on the record, made by the actual head of Google's quantum research division, discussing an actual published result, and it reignited a physics debate that's been simmering since Everett first proposed the idea over 70 years. Ego. Naturally, skepticism followed almost immediately, and this is where the story gets genuinely more interesting than the headline alone. Critics inside the physics and computer science community pointed out that random circuit sampling, while a legitimately hard problem for classical computers, is also, by design, not a particularly useful one. It doesn't cure diseases, model new materials, or solve any practical problem a business or hospital actually has. It exists specifically to demonstrate raw speed on a benchmark built to favor quantum hardware. That criticism had followed Google's supremacy claims since 2019, and it hadn't gone away just because the chip got bigger and faster. So in 2025, Google's research team responded to that exact critique with something new. They introduced an algorithm called quantum echoes, built around a real physics measurement called an out-of-time order correlator, a tool physicists actually use to study how information scrambles through complex quantum systems, directly relevant to real molecular and material science research. Running on Willow, quantum echoes reportedly completed this calculation roughly 13,000 times faster than the best available classical methods. But the detail that matters more than the speed number is this. Unlike random circuit sampling, this specific result could be independently checked against a real physical experiment using nuclear magnetic resonance techniques in an actual laboratory, giving outside scientists a genuine physical way to verify Google's claim instead of simply trusting an internal benchmark run entirely inside Google's own facility. Industry analysts have called this the first verifiable demonstration of quantum advantage, a claim that's arguably far more consequential and far harder to dismiss than anything the company had published before. Naturally, a claim this bold, coming from the head of one of the best-funded quantum labs on the planet, did not go unanswered by the rest of the physics community. And this is where the real scientific debate actually gets interesting. Harvard physicist Jacob Barandas, who has proposed his own alternative formulation of quantum mechanics that doesn't rely on multiple branching universes at all, raised a pointed and genuinely difficult objection to Neven's reasoning. His argument, in essence, was this: if quantum speedups like the one Willow demonstrated were truly powered by computation, spread across countless parallel worlds, you would expect to see that kind of dramatic advantage showing up broadly across many different types of problems, not narrowly confined to the small handful of extremely specific benchmark tasks quantum computers currently excel at. Scott Aaronson, one of the most prominent theoretical computer scientists working on quantum computing today, has spent years publicly wrestling with exactly this tension, acknowledging that the many worlds interpretation offers an internally consistent way to think about quantum mechanics, while also being careful to note that it remains a genuinely unresolved philosophical and physical question, not something Willow's benchmark result definitively proves one way or the other. This is worth sitting with for a moment, because it's the part of the story that often gets lost. Neven's comment wasn't a scientific paper making a testable, falsifiable claim about the structure of reality. It was an interpretation, a lens through which one of the field's most senior researchers chose to make sense of a genuinely strange result, another equally. Credentialed physicists are entirely justified in interpreting that same data completely differently. That's not a scandal or a cover-up. That's exactly how legitimate unresolved questions at the edge of physics are supposed to be argued out in public, by name, with real reputations on the line. Meanwhile, Google isn't racing alone, and the competition happening around it is just as significant as anything coming out of Google's own lab. IBM, the same company that publicly challenged Google's original 2019 supremacy claim within days of its announcement, has continued building its own aggressive, transparent roadmap. In November 2025, IBM unveiled a processor called Nighthawk, featuring 120 qubits connected through 218 next-generation tunable couplers, specifically engineered to run deeper and more complex circuits, rather than simply chase a higher qubit count for headlines. IBM's stated target is bold. By the end of 2026, the company expects Nighthawk to demonstrate quantum advantage on an actual commercially useful problem, not an engineered benchmark built to favor quantum hardware. A claim that, if it holds up, would arguably represent a more consequential milestone than anything either company has produced so far. Alongside Nighthawk, IBM also introduced an experimental processor called Loon, designed specifically to validate hardware components needed for full fault tolerance, feeding directly into the company's stated at 2029 target for its first genuinely fault-tolerant system, a machine they've named Starling. This is what real competition at the edge of physics actually looks like. Not silenced whistleblowers, not classified data, not scientists reassigned in the dead of night. Two of the best-funded research organizations on the planet, publishing competing roadmaps in public, setting concrete dates, and holding each other accountable in real time in front of the entire global physics community and anyone curious enough to read the papers themselves. And here's why any of this should matter to you personally. Beyond the sheer spectacle of a company suggesting its machine touches parallel universes, if quantum computers keep advancing along this trajectory, they aren't destined to become faster versions of your laptop. They're built to solve a fundamentally different category of problem, one classical computers structurally struggle with. Simulating how molecules actually behave at the quantum level has direct, real-world implications for drug discovery, letting researchers model how a new medicine might interact with the human body before it ever reaches a lab bench, and for material science, potentially accelerating the design of more efficient batteries and solar cells. Google's own research team has specifically pointed to nitrogen fixation, the energy-intensive chemical process behind most of the world's fertilizer production, as a target application where a sufficiently capable quantum computer could eventually cut global energy consumption on a genuinely massive scale. But there's a far more sobering implication too, one security researchers have tracked closely for years, and it's not speculation. Quantum computers, once they reach sufficient scale and reliability, are expected to be capable of breaking many of the encryption standards currently protecting online banking, government communications, and private data worldwide. Security analysts have given this looming threshold an informal name, Q-Day, and current expert estimates place that risk somewhere in the 2033 to 2035 range, close enough that governments and financial institutions are already being told to migrate to post-quantum cryptography now, largely because of a real actively discussed strategy called Harvest Now, Decrypt Later, where encrypted data is being collected and stockpiled today by adversaries simply waiting for a machine powerful enough to unlock it years from now. So where does all of this actually leave us? Standing here in the middle of 2026, looking at a chip that's either brushing against the structure of parallel universes or simply doing brilliant, grounded engineering that got described a little too poetically. At a press conference, the honest answer is that both of those things can be true at once. And understanding why is more satisfying than any manufactured mystery could ever be. Let's connect every piece of this story back together, because that's where the real weight of it lives. In December 2024, Google's Willow chip solved a genuine 30-year-old problem in quantum error correction, proving in real hardware, not simulation, that scaling up a quantum system can make it more reliable instead of less, a result published openly in Nature for any physicist on the planet to scrutinize. That same chip then completed a benchmark calculation that would take one of the fastest classical supercomputers on Earth an estimated 10 septillion years, a number so large it makes the age of the universe look almost trivially small by comparison. The head of the lab that built it, a real named scientist with real credentials, looked at that result and offered an interpretation that reaches into one of the strangest, most contested ideas in all of theoretical physics. The possibility that reality itself branches into countless parallel versions with every quantum event, and that Willow's speed might only make sense if its computation is somehow distributed across many of those branches at once. Other equally credentialed physicists, people like Jacob Barandis at Harvard and Scott Aronson, one of the field's most respected voices, pushed back with serious, technical, entirely public objections. And in 2025, Google answered the broader criticism that its benchmarks were too abstract to matter by introducing quantum echoes, a result independently verifiable against a real laboratory experiment for the first time in the company's history. None of this required a cover-up to be worth your attention. It required exactly the opposite, an unusual amount of openness, competing labs publishing rival roadmaps in full public view, physicists arguing genuinely unresolved questions using their real names and real reputations, and companies racing each other toward concrete, dated milestones that anyone can check on later to see who actually delivered. IBM's own public roadmap is refreshingly candid about how much work remains. Fault tolerance, the point where a quantum computer can run large, complex calculations without errors piling up faster than they can be corrected, isn't expected to arrive until IBM's Starling system in 2029. Scaling toward a 2,000-qubit machine called Blue Jay sometime after 2033, Google has offered similarly measured internal timelines for its own large-scale error-corrected systems. Neither company is claiming the revolution has already fully arrived. They're claiming they've proven the underlying physics works, and that what remains is a genuinely difficult but fundamentally solvable problem of engineering and scale, which is a very different and considerably more grounded statement than any headline promising a chip has torn a hole in reality. And maybe that's the actual takeaway worth sitting with here. The real story of Willow doesn't need embellishment to feel enormous, because it genuinely is enormous. A machine sitting in a lab in Santa Barbara just proved, in hardware, something theoretical physicists had been trying to demonstrate since the 1990s. Its creator looked at the result and reached for one of the boldest interpretations available in modern physics to explain it, and instead of that claim disappearing into silence or getting buried, it triggered exactly the kind of open, rigorous public argument that real science depends on to sort good ideas from bad ones. Meanwhile, IBM is racing to beat Google to a genuinely useful quantum advantage by the end of this very year, and security agencies around the world are already treating the eventual arrival of a fully capable quantum computer as close enough to plan national encryption policy around. This is not a story that needed a redacted file or classified signal to become one of the most genuinely important developments in modern science. It just needed you to look at what actually happened. So here's what I want to leave you with. If Google's Willow chip really is hinting at computation happening across parallel branches of reality, even if that idea remains fiercely contested among physicists, what does it say about where this technology takes us next when IBM's Nighthawk attempts to prove genuine quantum advantage on a real-world problem by the end of this year? And when both companies are racing toward full fault tolerance before the decade is out, do you think Neven is onto something physicists will eventually have to accept? Or do you side with Aronson and Barandis, who argue the interpretation is running ahead of what the evidence actually shows? Drop your take in the comments, because this argument is not settled, and it is not going to be settled quietly. Subscribe and turn on notifications, because the next announcement from either lab could land within months, and when it does, you'll want to already be here to see exactly what it proves and what it doesn't.